Okay, recording in progress. So another kind of technical challenge with this work was that we had to decide how to evolve the matter. And at first we were thinking of using things like scalar fields that we already had in the code. But it turned out that it's really difficult to construct the initial conditions using scalar fields and things like that. It's much easier to just directly construct the energy density and the momentum density of the space-time from the initial conditions, and then evolve them directly. So you know how your energy density evolves and how your momentum density evolves, because you can use that the divergence of T mu nu is 0. So you can use this to constrain 4 components and how they evolve. But that's then not enough. You also need to define how the other components of the stress energy tensor evolve. And this is where all of these kind of exotic spacetimes often break down. So, you propose some warp drive metric and you say, okay, I need this matter configuration. But then, in a time evolution, is that stable? It depends on the equation of state, essentially, of that matter. And as far as I know, there's no equation of state that supports a warp drive spacetime. So it will inevitably evolve away from this nice metric that Alcubierre wrote down into something that kind of disperses or that collapses into the center. And so that is a feature as well as a bug. So the actual Alcubierre metric itself, if it just kind of stayed there moving at a constant velocity through the space, it wouldn't actually give you any gravitational waves. But if it collapses and does something dynamical, then that's going to generate some gravitational wave content. So in a way, the fact that we don't know a good equation of state to keep this stable, is a good thing if you want to just generate gravitational waves. So what we do for the matter is we basically assume roughly a stiff equation of state. So in the paper, there's some justification for this, but it's really a bit of a hack, just because it was the thing that worked and the thing that was easy to implement. And then saying that the anisotropic stresses just effectively are damped and just die away in time. So if we prescribe things in this way, then everything we do is consistent with the Einstein equations. We evolve things forward in time consistently. We don't break the constraints or anything like that. But of course, then a lot of what we conclude is necessarily, potentially dependent on these choices of the matter equation of state. And so, we can't say that what we see is necessarily the right thing, or is it, how generic is it? So we have to do more work to try and understand to what extent what we see is kind of a generic behavior, or whether it's kind of specific to this particular setup for the matter that we've chosen. But okay, as I say, it was supposed to be a kind of quick, fun project. So we just do what we can. And so, now I will show you some of the results. So this is the extrinsic curvature K that I was saying about before. And so the ship is moving up in this direction. And so you can relate this to what I showed you before, where you have this region of positive K ahead of the ship that's collapsing, and the region of negative K behind that's expanding. And so I'll play this and you'll see what happens to those regions. So what you can see is that it's very bad for the people who are in the center. So these waves of positive and negative expansion just come in and are probably going to tear anyone in the ship apart by tidal forces, right? So this seems like it would be a very bad event for people who were in the spaceship. You can't take this movie too seriously. So as I said, the evolution of the extrinsic curvature is quite influenced by what gauge you choose. And so to some extent, this, well, like all things in a numerical relativity simulation, this is not a gauge independent quantity, right? So when we see it kind of, I'll play it again, we see it kind of dissipating away, to the extent to which it decays to zero, we would need to look at all the other components to really understand what's going on kind of physically with the space-time. But I think it's probably safe to say that it's very bad for the people in the ship. Like, I think clearly a lot's going on when the bubble collapses inwards. I think, it's definitely, definitely bad news to be in a collapsing warp bubble. So yeah, so I was saying, you can't trust in a way the extrinsic curvature. We have to extract quantities that are kind of physically meaningful. And as when we do gravitational waves from a compact binary, we look at the Weyl scalars, right? We identify the Newman-Penrose scalars and projections of the Weyl curvature onto tetrads. And so we can look at the evolution of the Weyl scalars where, in the center, again, this doesn't necessarily tell you anything kind of physical. It tells you some stuff is going on, but it's not easy to interpret. But far further away, where the space-time is essentially flat, then you can identify it with some gravitational wave content. So let me play this as well. So it's kind of a little bit delayed compared to the extrinsic curvature. So that's why I said that the extrinsic curvature, I think, is mostly kind of a gauge effect and not necessarily kind of physical gravitational wave content. So you see these kind of dark and light stripes. This is really the sort of the gravitational wave content that's coming out from this collapse of the warp bubble. And then when it reaches some radius, we can extract this and look at the waveforms. So because it has cylindrical symmetry, so if we align the tetrad axis with the direction of motion, then we only get modes for which m is 0. I think that's, I'm saying that correctly. So yeah, right, exactly. M is 0. So we have the 2-0 mode, the 3-0 mode, and the 4-0 mode. And I mean, they look kind of weird, right? So they, well, not so weird. I mean, you have some oscillations, you have some reasonably well-defined frequency for the signal. This is something that, potentially if it was loud enough, well, you could see. So, well, we'll come back at the end to talk about detectability, because there's some conclusions on that based on what we saw. But you can see that we only really did low velocities, low warp speeds. So this is 0.1 c, where c is speed of light, 0.15, 0.2. We did actually get it working up to 0.5, and we think it probably would work up to v is 1, but it starts to require really high resolution. And so we already kind of felt a bit guilty spending computing time doing this project, so we didn't push it too far. And the waveforms are fairly similar for different velocities. They have the same sort of morphology. It's just the amplitude you can see is kind of growing, roughly proportionately to the velocity. Yeah, so then we have this interesting question about what happens to the matter. So we start with here it's negative energy density. So the black bits are negative and the white bits are positive energy. And so we were kind of interested to see, what would happen with the matter. So let me play this. So what you see is that there's this sort of shell of positive energy density that forms within the negative energy density. And then that kind of propels the negative, a sort of dark wave of negative energy density kind of propels it outwards. And this is consistent with something that was proposed already by Bondi in 1957, so really a long time ago, where he was studying what would happen with negative and positive masses, and the fact that they would kind of attract and repel each other in a way that would accelerate them away, and lead to them kind of pushing each other along. And so this is kind of reminiscent of that effect. It seems like, yeah, I can play it again. There's this, this positive wave inside sort of drives it outwards. But you can see that there are kind of alternating waves of positive and negative energy density, leaving behind this kind of remnant that appears to be kind of stable, which is quite interesting, that you can get some kind of stable matter configuration where you have both positive and negative energy densities. I don't think it's necessarily obvious that you could settle down to some stationary state, albeit, as I said before, that this is all quite dependent on what we chose for the equation of state of the matter. Yeah, so let me tell you a little bit about the fluxes. So for the energy of the gravitational waves, you can see that there's just some increase. So this is the integrated energy. So in this case, it's in the 2-0 mode, but you get the same thing for the total energy radiated in gravitational waves. So there's some increase as the wave passes the radius where you're extracting. You get some increase, and then it kind of saturates. But you're always radiating, obviously, positive gravitational wave energy. But in the energy of the fluid, the energy of the matter, you get these kind of alternating waves of positive and negative. So this isn't the flux. This is really the integrated flux. So you really here you've had some, like, this is this wave of negative energy density that's going outwards, so that the total energy is negative. And then your wave of positive energy goes out, and so that decreases you again. And it oscillates as you get wave after wave of kind of positive or negative energy density. And so, the question that we were asking at the beginning was, well, what's the end state? Overall, do I radiate a load of positive energy? Do I end up with a negative ADM mass? What happens? And so we can sort of zoom in and look at the end of these plots that show the energy fluxes. So particularly the one on the right is at the end. The matter overall has radiated a negative amount of energy. And the gravitational wave is overall positive, but it's tiny compared to the matter radiation. So what this tells us, if you have to think about it, if you've radiated totally a negative energy, so that means that your energy has increased in that volume. So we actually go from 0 ADM mass to a slightly small positive ADM mass. So we don't actually go to negative ADM masses, which I found quite interesting. And I wonder if that's something that you can show is a kind of generic effect of the dynamics of these kind of spacetimes. Maybe it isn't. Maybe it's just specific to this case we studied. But it's quite an interesting question to ask. Yeah, so the thing that you might want to ask, the real $1 million question is, can we detect, when you're going to LIGO this afternoon, should you be telling them, guys, you need to be looking out for these warp ships? And the answer is probably not. So the amplitude actually is quite strong. So the amplitude is good, but the frequency is bad. So that's the kind of summary. So the frequency of these waves, I've actually managed to kind of chop off the legend, but you can see that they have kind of 1 unit, where if this square is 1 unit. So the wavelength is about 1 unit. And my unit is R. So what's R? So R is the size of the warp bubble initially. So in the paper, we use as a kind of reference value that R is probably something like a kilometer. So if you go and Google, like, how big is the Starship Enterprise, or a specific model, the Enterprise E, if you want to be really geeky, you'll find out that it's something like 684 meters or something like that. And so the warp bubble is of order a kilometer in size. And so if you convert that kilometer in geometric units into a frequency, it gives you something of the order of hundreds of kilohertz. So that's obviously much higher frequency than LIGO is sensitive to. And so, yeah, in principle, if these ships kind of are flying around with these warp drives, we would need a detector at a higher range of frequency to be able to see them. So we did have people say to us, oh, well, but if you make the warp ship bigger and bigger, if you have an Earth-sized warp drive, then you start maybe to be able to be in the LIGO band, or like a Death Star, I guess, or something like from Star Wars. So, I mean, yeah, I guess you can always play that game and say that we've ruled out Death Stars in the LIGO data, but I think, yeah, I mean, you can take this anywhere you want. But in terms of the amplitude, it's quite interesting because you can work out. So assuming that we did have a detector at the right frequency range, what would the amplitude be? And so we have this number 0.01 over R at a distance of R.
10 minutes.
Oh, 10 minutes. Okay, that's good because I haven't got much left. Yeah, so if you put this into kind of physical numbers, again, for the 1 kilometer sized warp bubble, you end up saying that I think we could detect them to something like a megaparsec, which is pretty close. I mean, it's pretty far actually, right? So it's way beyond the galaxy. So we'd definitely be able to see anything happening in the galaxy with warp ships. Well, definitely. So Tim told me that I can't say definitely for things like this because you have to do a proper analysis and all of this kind of stuff. But I mean, it would be a very strong strain signal at that kind of distance. It would be 10 to the minus 21. So similar to the kind of LIGO sensitivity. Yeah, so it's a bit of a shame that we can't detect gravitational waves with LIGO for the moment. But yeah, if you like Star Trek Voyager, then there's this point at which they say, it's not about the destination, it's about the journey. So here are my movies again. So we had a lot of fun doing this project. And it is a bit silly, but it's also has some definitely had some interesting technical points in, and also had some interesting physics to try and think about what was going on. So in summary, I wanted to say to people, if they're people earlier in their careers, don't give up on your crazy ideas. But then I did actually wait until I got a permanent job before I put this on the archive, which I think is probably not such a bad idea. So LIGO has not ruled out post-warp civilizations yet, although, you can argue about it. But future high-frequency detectors, maybe will be able to, which is perhaps a motive. So there are groups looking to build higher frequency detectors, I know, for things like primordial black holes and cosmological signatures. And they can now argue that they would also be able to rule out or confirm the existence of alien warp drives. So that's quite nice. So there are still some questions open. So I think I'm a bit exhausted with warp drive. So I don't think I'm going to answer these. So if anyone else wants to, I will make my code public and they can go and investigate these questions. So yeah, is this behavior generic to negative energy space-time? So in particular, what's the impact of choosing different equations of state for the matter? And also what happens beyond V is C? So in principle, once you go beyond V is C, once you go past light speed, you should be able to form closed time-like curves. So you can imagine that, how does that manifest in a simulation? Do you get some kind of elliptic regions forming? Do you get some kind of pathologies? I think that would be quite interesting to think about, but also quite challenging because As I said, it did require quite high resolution, and I think especially in these cases you would. So you probably want to move to a code that's adapted to the cylindrical symmetry of the problem, which would allow you to go a lot further. And that's it. So just to say, I did post this on Twitter. So I never post anything on Twitter. But I thought that this was so fun and something that people on Twitter would probably like, that I decided I would put it on Twitter. And so if people are on Twitter and can, I don't know, do whatever you do on Twitter when you like something, repost it or like it, that would be great. It would be fun if we got kind of picked up by Captain Kirk or someone like that. That would make me very happy. And I'll stop now and take questions. Oh, I see there's actually some questions in the chat.
Yes, we ask the online one first, maybe.
Yeah, do you want me to answer the questions?
Yeah. You could answer the online one first. I think there's just one.
Yeah. Hi, Katy. Thanks for the talk. Do you think that the numerical implementation would be easier in other coordinate systems? Yes. Yeah. So I think definitely, using Cartesian coordinates was not a good idea. As I said, this was kind of meant to be a kind of quick project where we, we'll just put it in and see what happens. And then it ended up being a lot longer. But if I was to start from the beginning, I wouldn't use our code. I would use something that's more adapted to the symmetry of the problem, which, as I say, is cylindrical. So I guess you could use Zach's code, right? So which has the ability to be adapted to cylindrical coordinates. Or you could do a kind of cartoon reduction. So actually in our code, we have the ability to do a cartoon reduction to 2 dimensions. But I didn't get that integrated with the warp drive code. But in the future, if I had the strength, that's probably the way that I would go. Yeah.
How many questions in the room? Okay.
Hello, Katy. Can you hear me?
Yes.
Okay. So based on my understanding, it seems you started with the warped spacetime and then it became to Minkowski, like it radiated away and became Minkowski.
Yeah. So further away it is Minkowski. So in the center you actually do get some kind of like remnant. I don't know, you could call it like a warp fluid star. I don't know, I could probably make up some cool name for it if I thought about it harder. But you get some blob of this matter, like whatever it is, the warp fluid, and it's curving the space-time because it's matter, it's got energy, and it does seem to be stable. So and from our analysis, that has some overall, it has a positive mass, so it has some positive and negative energy density in the matter, but the total kind of ADM mass of the remnant space-time appears to be positive, a small positive value. So it doesn't go completely to Minkowski, it doesn't completely dissipate, there is still some remnant there.
Yeah, because I was wondering if you ever thought about doing the reverse, where you start with the flat and you try to create some kind of warp geometry.
If you could do that, you would make a lot of people very happy. So I think, yeah, forming a warp drive dynamically, I mean, that's a really good point. So, in all of these, I mean, we think about this in terms of like modified gravity theories as well, right? Where we think, not only can we just kind of write down a solution, but can we get to that solution dynamically? And in the case of the warp drive, you're relying on, the aliens to have some kind of clever technology that somehow confines this fluid in the right distribution to drive the warp drive forward. Kind of similar to, well, I think for wormholes, some configurations are kind of stable, but I don't know if you can form them dynamically, right? So if you can think of a way to form these dynamically, as I say, that would be amazing. But I think it's quite hard. Yeah.
Thank you.
Any more questions in the room? I've got one question. Mainly, so I'm not an expert in any of this, obviously. But when you said this is a gravitational wave sourced by the collapse of the rock bubble, is this anything that would look at all similar to collapse of other bubbles that you might have, say, in an early universe, some domain walls, anything like that?
Oh, yeah. That's a good question. I don't know because I actually don't think so I know that Eugene Lim was looking at kind of bubbles colliding. So I don't know if you put in something that was like normal matter, so no negative energy density, you just put this kind of ring of stuff and you let it collapse, you probably would get something a bit similar. So yeah, degeneracy with other signals is definitely something you would need to think about. But I guess I guess the real question is, does it look like a supernova? Because I guess that's the most kind of comparable thing that we know does exist. So I guess I haven't really thought about that, but yeah, you could definitely try and figure out if it's similar to something like a supernova. That would be cool.
Okay, thanks. There's one more online question.
Oh yeah. Which other options of gauge choices do you plan to implement? Yeah. So gauge choices can't help us just not destroy the ship. So I think the ship will definitely always, gauge is just gauge. So gauge is just coordinates. So we should see the same physical result, whatever gauge we use. But maybe you mean like other equations of state for the matter. So that's the hope, is that we could develop some equation of state for the fluid that would somehow support the warp drive configuration and allow it to be stable. And there was something we thought of in the paper. It's like a footnote in the paper where we talk about what you would need to do for that. And it seemed like you would need some higher order derivatives in space and time. So you need some third order derivatives to try and support it. We made this kind of hand wavy argument about it. And that often creates ghosts and creates problems, we know from modified gravity theories. But I mean, there's nothing that says that you can't find something that works. It's just we couldn't think, like we weren't clever enough to think of it. And if we were clever enough to think of it, then you have problems about whether it's well posed or not, or whether it's going to be stable. So we just did the thing that was simplest and that works. But yeah, if you can come up with something else, again, as I say, you'll make a lot of people very happy.
All right, so then last call for any questions? No questions in the room. Let's thank Katy once more. Thank you very much. I'm not sure if you'll be around a little bit longer or if you have any more time for questions. Otherwise, people, I guess, can send you a Twitter message or retweet your tweet.
Of course, yes, definitely. Thank you.
Thank you. And for us local here, we have coffee outside again, and we'll have the next talk by Henry Vitek at 10:30, also remote. It is my pleasure to introduce Henry Vitek, who will do a presentation on the molecular